You ever see one of those massive cargo ships and it's just leaning to one side? It looks kind of wrong, right? Makes you wonder, is that thing in trouble? Is it about to tip over? Well, today we're going to figure out exactly why that happens, and more importantly, how the pros fix it. Okay, let's get into it.
So, here's our game plan. We'll start by figuring out what a tilt really is. Then, I'll show you the one simple formula that rules everything. After that, we'll learn a really cool method to make the calculations easy, run through a real-world example, and then, for the final boss, we'll tackle how to bring a listing ship perfectly upright again.
All right, first things first. A ship tilting isn't always a bad thing. But there's a world of difference between a ship that's just rolling with the waves and one that has a serious, persistent problem.
And it all comes down to these two words, heel and list. A heel is totally normal. A huge gust of wind hits, or a big wave rolls under it, the ship leans, and then it pops right back up. It's temporary, caused by something outside. A list, though, that's different. That's a stubborn, constant tilt caused by an internal weight problem, and it's not going anywhere until someone fixes it. And that list is what we're focused on today. This shows you exactly what's going on. On the left, you've got a perfectly happy balanced ship. See that G? That's its center of gravity, right down the middle. But on the right, maybe some cargo was loaded unevenly. That G gets pulled off to the side, and when that happens, the whole ship has to lean over just to find its balance again. That lean, that's the list. So how in the world do you calculate that? How do you know exactly how far a ship is going to lean? It sounds super complicated, but it all comes down to one beautiful, elegant piece of math. I like to call it the golden formula.
The whole secret, the entire key, is understanding that center of gravity. It's like a giant balancing act. Every time you move weight around on the ship, you're shifting that balance point. All we need to figure out is, 1, how far that center of gravity shifts sideways, and 2, how stable was the ship to begin with. That's it. Those are the only two pieces of the puzzle.
Now, don't let the geometry on screen fool you. This little triangle is actually our best friend. It turns this big physical problem into simple trigonometry. That angle at the top, theta, that's our angle of list. And it's created by just two things, GG1, which is how far the center of gravity shifted sideways, and GM, which is basically a number that tells us how stable the ship is.
And here it is. The tangent of the list angle equals GG1 divided by GM. That's the whole thing. If you can find those two values, that sideways gravity shift and the ship's stability, you can calculate the exact angle of list every single time. This is the bedrock of everything we're about to do.
Okay, so we've got the formula. Awesome. But how do you find GG1 and GM on a real ship with cargo being loaded and unloaded all over the place? For that, we use a simple but really powerful analogy, the double accountant method.
Just picture it. You're an accountant for the ship, but you have to keep two separate ledgers. One ledger tracks every weight that affects the ship's up and down stability. The other one tracks all the side-to-side forces that are trying to make it lean. If you can keep both of those books perfectly balanced, you're in complete control.
So, here are our two ledgers. First, the vertical table. This is all about stability. We measure how every piece of weight affects the ship vertically, from the keel up. This is how we find our final GM. Second, the transverse table. This is all about the tilt. We measure everything from the center line, sideways. This tracks the tilting forces and gives us that all-important GG1. All right, enough theory. Let's make this real. We're going to take a situation, apply our two-table method, and solve for the final list, step by step. Okay, here's our first ledger, the vertical table. You can see we start with the ship itself. Then we add our new cargo. We've got 200 tons going on at a height of 4 meters and 100 tons way up at 10 meters. We do the math, and it spits out our final stability number. Our GM is 0.5 meters. Just like that, half of our formula is solved. Now on to our second ledger, the transverse table. This is about the sideways push. That 200 tons of starboard cargo is 5 meters off-center, creating a tilting force of 1,000. The port cargo is creating a smaller force of 400, so which way is it going to go? Well, starboard is winning with a net tilting force, or moment, of 600. We divide that by the ship's total weight, and there it is. Our GG1 is 0.113 meters. And now for the grand finale.
We take the two numbers we just worked so hard to find, we plug them into our golden formula. That's 0.113 divided by 0.5. You run the numbers, and what you get? A final list of 12.7 degrees to starboard. We went from a complex problem to a precise, definite answer. Pretty cool, right? Okay, so you've totally mastered calculating the list. But what if the problem is flipped? What if you step onto a ship that's already listing, and your job is to make it straight again? This is the final challenge. So, let's put you in charge. You look at the gauges, and your ship has a 5-degree list to starboard. You've got a bunch of heavy steel plates you can move around. The question is, how many tons do you have to shift to bring her perfectly upright? The logic here is actually pretty slick. We just work the whole problem backwards. We already know the angle of list, it's 5 degrees, so we can use our golden formula to find the invisible problem, the GG1, that hidden shift in the center of gravity. Once we know that, we can calculate the total tilting force that's causing the problem. And once you know the exact force you're fighting, you can figure out how to beat it. So, when we work it backwards, we find there's this invisible force of 315 ton-meters pushing the ship over to starboard. And that makes our job simple. All we have to do is create a perfectly equal and opposite force. We need to move just enough weight to create a 315 ton-meter moment to port. The two forces will cancel each other out, and the ship will snap right back to a perfect 0-degree balance. So there you have it. You now know the science behind a listing ship. You know how to calculate it, and more importantly, you know how to fix it. You understand the hidden dance of weight and balance. But all of this is in calm water. The real question is, what happens to all this beautiful math when a storm rolls in and the waves start to crash?